So in today's session, I'm going to discuss about 2.5, which is transfer function. So last week, in week 6, we have finished 2.4, which was about the um, Laplace transform. Okay, so a lot of things we have learned about Laplace transform. And then we are going to use the Laplace transform in another part of the second topic, mathematical modeling topic ni. Which is the 2.5 transfer function. So transfer function is important in control system design, okay? Because in control system design, we represent our control system block diagram in the form of transfer function inside. All right. So the transfer function. What does it mean by the transfer function? So transfer function, as you can see in this the screenshot. I've taken it from the textbook. So the transfer function of a linear system is defined as the ratio, ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. Meaning that ratio means output Laplace transform, output variable Laplace transform divided by input variable Laplace transform. That is the transfer function. Okay, and another condition is all initial conditions assumed to be 0. So all initial condition must be 0. Okay, so that are the two things that we are going to that is determines what is actually the transfer function. It is defined as the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable with initial conditions assumed to be 0. Right? So let me just write a bit. Transfer function I hope you can see here. Transfer function of a linear system. Now we are talking about linear system. Linear system only, which is the linear time invariable system, LTI system. Okay, so this transfer function we are talking about is valid only for the linear system, which is linear time invariant system. So when we talk about LTI, suppose the system should be linear, and also nothing is stationary or constant parameters. Constant parameters. Parameters tak boleh berubah-ubah. Dalam kes ni, kita perlu consider yang linear system saja. So it is not refer to the, so transfer function that we are talking about is not refer to the time varying system. Ada satu lagi, time varying system, which is a non-stationary system. Non-stationary system, which is varying parameters lah. Yang ni, yang time varying So we are not going to talk about this. Actually, we will only consider the linear time invariant system. Okay, so what is the definition again? What is the definition of the transfer function? It is, so transfer function it is a ratio ratio of the Laplace transform Laplace transform ada juga Laplace transform of the impulse response of the output variable. Boleh juga. So dalam buku teks, ratio of the Laplace transform of the output variable to the Laplace transform of the input variable. Ada lagi sambungannya. With all initial condition assume to be 0. Okay, in the question, basically you will be given the initial condition, like y naught is equals to 0. Okay, RT input is equals to 0. That is the initial condition we are talking about. Okay. All right. So if we have a block diagram, of the control system, single block diagram like this. Let's say the transfer function is GS. GS is the Laplace transform. So, of course, at the output, I have the YS at the output, and I have the input variable of RS, which is Laplace transform of the input, and YS is the Laplace transform of the output, and GS is the transfer function. So, Laplace transform means, transfer function means the ratio. Transfer function GS means the ratio of YS divided by RS. With the initial condition is assumed to be 0. Okay. So let us consider the previous example. Which is a spring mass damper system. Let us consider the case of the previous example. Let us consider the case of the spring mass damper system with zero initial condition. We have seen this equation actually in our previous discussions. Okay, let us consider previous example of spring mass damper system, which is the equation of the spring mass damper system given as ms square ys, okay, plus bs ys plus k ys equals to r. This r is rs. Let me put this a bit shift. This one equals to RS. Okay, right. So for that particular equation, in the form of Laplace transform with output, ys, we have the output ys here. This is output. So for this particular equation, differential equation that has been transformed into the Laplace transform form, the differential equation in the form of Laplace transform of spring mass damper system like this, it has input of Rs and output of Ys. So Rs here is input. So we are going to derive the Laplace transform of this particular equation. Okay. So this is the equation with initial condition. Actually, for this particular equation, it was based on the ms square ys ms y naught plus bs ys minus by naught plus k ys. It was like this actually, equals to 0. So with the initial condition, meaning that some initial condition is 0, which is y naught is 0 for this case. So it becomes like that lah. It becomes the equation which is the above one. So if you take this y naught as 0 and this by naught also 0, the term left is ms square ys, bs ys, and kys equals to rs, which is in this case 0 initial condition. So ys is rs is also 0. So this is 0 initial condition. So we have this equation with 0 initial condition, which is referring to this equation. All right. So from that equation, we rearrange it because we want ys, right? We want ys. We rearrange this equation like this. Actually, this rs is not 0. Why is this rs is 0? Actually, this rs is not 0. The input is not 0 actually. Sorry, this is plus k y s equals to rs. Why not only 0? Only why not is 0. Rs is input. Okay. So we rearrange it to the equation, which is this one, to clearly see the input and output relationship. So we have Rs as input and Ys as output. Ada orang panggil tu nak suruh give Viva. Saya dah bagi tahu dah sepatutnya. Okay. Masih lagi nak tanya. Okay, tak apa sekejap Saya pause sekejap. Alright. So we have reached up to this equation. Okay. So how to get the transfer function? This is a ratio, right? The transfer function is the ratio of ys to the rs, right? So what we do is, transfer function is output by input, meaning that it is ys divided by rs. So that is gs, okay? So from that equation, gs is 1 over ms square plus bs plus k. Okay, so 1 over ms square plus bs plus k is the GS, which is the transfer function of the spring mass damper system. Okay, so this is the transfer function of the spring mass damper system. So that was about the mechanical system. Similarly, we can do for the electrical system. Which is let us consider another case of the deriving transfer function of this particular RC network. So this is RC network. So in this RC network, of course, we have R and C. Okay, so it has input and output, which is input is V1 and output is V2 as a function of time. Okay, if you closely look at this circuit, actually you can just rearrange this circuit just like this, which is the circuit that you might familiar with, right? Have you seen this circuit before? So input is, let me just rewrite again, V1 T, V2 T, plus minus, plus minus. So we have voltage input across R and C, okay? And we have voltage output V2 across C. All right, for this particular case. Then we use, of course, as usual, we use Kirchhoff voltage law or voltage equation, which is input, in this case, input as a function of S, which is Laplace, function of Laplace transform, okay, is defined as the R plus 1 over CS. Okay, and the current IT is IS. So that is the first equation. How about the output V2? So the output V2 is current. So VS, V2, V output is across C, right? So the only impedance is capacitor, which is, this is the second equation. So we have input V1, this equation, and another output V2, which is this equation. Now we want to obtain the transfer function of this particular circuit. Then obtain transfer function of divided by input. So transfer function is output divided by input. If we represent the transfer function as GS, so simply it is Vs V2s divided by V1s. Okay, so in this case, simply V2 divided by V1, I cancel, and then we get as a function of impedances only, RCS plus 1. Ni saya short circuit. If you want to calculate, you just simply calculate this by dividing V2 divided by V1. All right. Let's say in this case, RC is time constant, which is this is normally R and C is constant. So in RC, RLC, RL circuit, okay, basically we consider the R and C is constant, which is the time constant. So in terms of circuit, basically what we see is function of the exponential function. So basically it is decaying exponential for the circuit that involve a capacitor, inductor. All right. So RC is assumed as the time constant. Then we can just replace RC with tau, tau S plus 1. So that is the transfer function of the this circuit. Of this, actually this is a voltage divider circuit. So this is the voltage. So this is actually the voltage divider circuit. All right. But up to this stage, actually we can still simplify this. Hope actually we want to simplify this up to, remember when we talk about when we do the transform and we need to do another transform to back to time domain. All right. So actually we are trying to rearrange this transfer function equation to the simplest form so that we can easily transform it into, retransform it to the time domain, which is the inverse Laplace transform. So let's say for this particular equation, we will need to rearrange it to the equation, which is we can say 1 over S something like that, right? Okay, so we decompose this. So we will try to decompose it. Let me just show you how to decompose this. To decompose this equation to pole and zero form, to the simplest form that we can translate. So, okay, so that we can translate what is the meaning of that equation. So basically 1 over Ts plus 1. To simplify it, what I do is normally we try to cancel tau here. Okay, so by the denominator here, I divide by tau so that I can cancel tau. Okay, so that I can get S only. All right, I want to get S only. So here, when we multiply with 1 over tau for the numerator and multiply 1 over tau for the denominator, it becomes the numerator becomes 1 over tau and denominator becomes S plus 1 over tau. See? So here, the numerator is, remember, PS. Numerator is PS, which is something about zeros, right? So denominator is QS, which is the pole. So we can say that for this particular equation, which is GS equals to 1 over tau divided by S plus 1 over tau, we can say that for this characteristics equation, okay, the denominator is, we call it as the characteristic equation. For this characteristic equation, we can say that there is a single pole. Okay, so S equals to negative 1 over tau is single pole. Single pole of the GS. So this circuit is actually the voltage divider circuit. You remember the voltage divider circuit? It should be V2 divided by V1 is equals to Z2 divided by Z1 plus Z2. Ingat tak? Sebelum ni ada juga. Saya nak teruskan. I'm going to continue. So there are two methods we can obtain the transfer function of the system. Okay, two methods we can obtain the transfer function of the system. Of obtaining transfer of the system, which is the first one that we will cover in this lecture, is the block diagram method. The block diagram reduction method. And the other one we call as the signal flow graph. The other one is signal flow graph. Basically, in this lecture, we are not going to talk further about signal flow graph. So we amend this. For the scope covered in this course, we are going to talk about the block diagram reduction, which is actually if we have a multiple block diagram like this, okay, and we have another feedback block, right? So block diagram reduction, if you have this GS, HS, okay, J, so this is J, H, JS, this is plant, this is process, another process, this actuator, and this is what we call controller, for example. So we can combine this together in a single block diagram. Okay, in a single block diagram like that. That is what we call as the block diagram reduction. All right. So why do we use the block diagram reduction method? It is because it is easier to visualize. People used to biasanya kita akan rasa lebih senang lah. It makes easier for us if we present something in the form of image, right? So otak kita bila ada proses maklumat biasanya lebih cenderung untuk proses image, right? Okay, so it is easier to visualize the control system interactions lah in terms of the input and output by using the block diagram, by using the block diagram. So it is easier to visualize the control system interactions. Macam mana kita nak lihat bila kita put some disturbance at the input, what happen to the output? If we putting one magnitude of impulse response at the input, what happen to the output? That sort of interactions, input and output, it can be easily visualized if you use the control system block diagram. So block diagram reduction is what it means by I've just shown you before. We reduce multiple blocks of the transfer function into one single block. So interactions in terms of input and output. So in control system, basically, if we have this sort of transfer function block diagram, if we have a block diagram with the transfer function like this, okay, we can examine the characteristics of the system easily. So just by observing what is the action that we put at the input and what it becomes at the output. Okay. So in control system design, okay, in control system design, the objective is actually to control the output that we design. So in control system design, actually, we try to understand the output, try to control the output that we desire. Kita nak temperature tu maintain dekat 24 degree C. What we do is we model the system and then transform the system into in the form of transfer function. So for that particular model, any input that we give, it will affect the output. Okay. So let's say if I have this sort of diagram that shows the transfer function, GS, it has input of XS, at of sex, and YS at the output. So what we do is actually so far through the mathematical modeling, Laplace transform, and the transfer function at the end now. So by knowing the transfer function, by knowing ds, this transfer function, we can actually we can give any input to the system and then observe what happened at the output. Observe what happened at the output. So we can, so at the output we can obtain we call it as output response. All right. Okay. Now let's move on to this example. Too familiar with the equation or mathematical modeling that involve the transformation from time domain to frequency domain or S domain, and after that we should rearrange the equation in the form of Fs here, that is easily we can transform back to time domain. Okay, we try to solve the equation of Fs in the form of this type of this sort of equations lah. Okay, so that we can just use the table to get back the function in time domain. So this is an example 2.2, which is we try to solve for the differential equation of this one. Okay, I zoom full screen mode here. So we let us consider a differential equation of this one. Second derivative of y plus 4, first derivative of y, 4 dy dt plus 3y equals to 2rt, where the initial condition is given, which is y0, y at time 0 is 1. The first derivative of y at time 0 is 0, and rt is 1. Okay, so that is the initial condition. So this is supposed to be the linear system, for example. So given the initial condition, we want to do the Laplace transform and then obtain its transfer function. Okay, obtain its transfer function. So what we do actually is we try to separate S ataupun YS. We try to separate YS so that we can get the transfer function in the form of YS divided by RS. For this case, sebenarnya dia sebenarnya nak tunjuk solution for differential equation. One of the thing that in mathematics we should familiar with. I would like to stress here for all of you that you will need to familiar with rearrange the equation of this polynomial, for example. For this one, we want to transfer to this form. What we do is we use the partial fraction expansion. Partial fraction expansion. Okay, from this form to this form actually. Okay, from this form to this form, we need to be familiar with partial fraction expansion. So I am not going to teach you how to do the partial fraction expansion in any mathematics based calculation based questions, because I hope that you already get exposure to those basic maths. In engineering maths, you have engineering maths 1, engineering maths 2. I hope this topic is already covered in the engineering maths. Okay, so from this equation, we do the Laplace transform of this equation. Basically, we get this by referring the table, Laplace transform table. So it's always important for you to refer to this table. For the easiest one is just memorize it. Okay. The easiest way is to memorize it, or you can just always have a look at it, to check it every time until you memorize it. Okay, I hope so lah. Saya sendiri pun tak ingat sebenarnya. Okay, so we can do the transformation to the S domain for this particular equation in time domain, which is we get the Laplace transform of this equation, which is S square YS minus SY at time 0, okay, plus 4SYS minus Y0 plus 3YS equals to 2RS. So this is the Laplace transform of this equation. So we get this equation in time domain. Sorry, we get the time domain equation in the form of Laplace transform, which is the S domain or Laplace domain. Then we can rearrange the equation because we want the YS, we want the output as a function of S, right? Output as a function of S. So here we get YS equals to S plus 4 divided by S squared plus 4S plus 3 plus 2 divided by S squared, S times S squared plus 4S plus 3. So similar terms here for S squared plus 4S plus 3, similar term to this one. Basically, for these two terms, we are going to transform it into this term, into number divided by S plus something, so that we can easily transform it back using this table. Okay, in the form of this. which is exponential function. Okay, 1 over s plus constant. All right. So how do we do this? How do we do this? I hope you all know on how to use the partial fraction expansion. Partial fraction expansion. Okay, for example, let me show you. Okay, for example, 2.2 here. Oops. For example, 2.2, for this particular equation, in example 2.2, how do we transform the equation of ys s plus 4 divided by s square plus 4s plus 3 plus 2 divided by 950 dah. S square plus 4s plus 3. Macam mana kita buat ni? Kita menggunakan partial fraction decomposition ataupun partial fraction expansion. What we do is do like this, which is we assume some arbitrary or some constant, which is a divided by s plus 1, another constant b divided by s plus 3. Kenapa s plus 1, s plus 3? Sebenarnya yang ni kita boleh pecahkan lagi ya. Yang ni boleh dipecahkan kepada s plus 1, s plus 3. Similarly for this one. Similarly for this one. Okay. So a, b plus c divided by s plus 1 for this term, the second term. Plus d divided by s plus 3 plus e divided by s. Okay. So we have all terms for the denominator here has been transformed into s plus 1, s plus 3, s plus 1, s plus 3 and s. Kalau you darab balik yang bawah tu, kalau you darab balik yang bawah, denominator ni, darab balik semua, you akan dapat balik yang atas ni lah. Okay. Alright. Now, once we get that sort of equation, we can simply do the thing that we are familiar with, which is for the first term, for this term, okay, a s plus 3, b s plus 1 divided by s plus 1, s plus 3, right? Let's say I'm going to show you an example of solving the first term, solving this. Okay, so we get the numerator, which is numerator. Saya tulis numerator, which is we get a s plus 3 plus b s plus 1. To find a and b, what we do is we try to make, let's say I want to make this term 0. How do I make this term 0? How do I make this term 0? Actually, this equation is equals to this one, the above one. Because I'm talking about this term decomposed into this term, then we want to find a and b. Okay, so we rearrange this equation to get the numerator, which is a s plus 3 plus b s plus 1. So the numerator is actually equals to s plus 4. So this numerator, okay, equals to s plus 4. So to find the A and B, basically what we do is we try to cancel, let's say I want to cancel this term. To make this term 0, what I do is by substituting S equals to -1, right? Saya substitute S sama dengan -1, saya dapat term ni 0. Bahagian ni 0, betul? Okay. So, let's say substitute S equals to -1, we get A -1 plus 3 plus B -1 plus 1, which is 0. So, S substitute by -1 and 4. Alright. So, of course, we can see that this term will be cancelled. And then we can get A. So here 2A, B is 0. B has been cancelled there, alright? B sebenarnya ada value tapi disebabkan term yang dalam kurungan ni jadi kosong. So this one 2A equals to -1 plus 4 is 3. So A is 3 divided by 2. Okay? A is 3 divided by 2. Okay. So it's 9:55 already. Let me pause. So here we have settled A, which is the first term. So we can just substitute. Actually, we got this. So we can just substitute A here. Alright. So basically next, let us consider B now. So for B, actually we still use the same equation here. For B, we still use this equation, but now we try to substitute S equals to -3 so that this term will be cancelled. Okay, so we substitute S equals to -3 for that equation, so that we get A -3 plus 3 plus B -3 plus 1 equals to -3 plus 4. So this term cancel, this term becomes 0, so that we got -2B equals to 1. So B here is -12 or 1/2. Okay, so we got A and B. All right. So how about another term? How about another term? We can do the similar thing to get another term. We can do the similar thing to get another term, which is in this case, you can just do the exercise lah. In this case, let's find C, D, and E. So the rest, C, D, and E. And actually, it is given that C, where is my C? Actually, C is -1. D is 1/3. And E is 2/3. Shortcut je. Shortcut ya. Nanti cuba kira balik. Alright. And then once we got C, D, and E, then substitute in the equation above, the equation YS, so that Okay, b s plus 3, b is -1, b is -½ huh? -1/2 s plus 3 plus c is -1 s plus 1 plus d is 1/3 s plus 3 and plus the final one 2/3 divided by s. Okay, so we got several terms here, which is this one is, let's say this is y1 terms. So next, this the second term, this is, let's say this is y2 terms, and also the other one here is y3 terms. So we get ys equals to y1 plus y2 plus y3. Let's say if we want to take the limit, let's say t approaching infinity for this particular equation. Sorry, after we got this form, okay, 1/s plus 1, sorry, 3/2 over s plus 1 plus -1/2 divided by s plus 3 plus -1 divided by s plus 1 plus 1/3 divided by s plus 3 plus 2/3 divided by s. So when we got that form, so we can just simply use the table, which is basically the exponential function. So we want to transform it back to the ft, okay, from fs to ft, which is based on this form 1/s plus a ni. So if we transform it back to the ft, we get e to the power of -at. All right, e to the power of -at. So we get yt as in the slides here. So yt is p/2 exponential -t minus 1/2 exponential -3t. So this is the first term, y1, plus -1 exponential function of -t plus 1/3 exponential function of -3t plus 2/3. That is yt. So once we get this yt, if we want to get, if for example t is approaching infinity, so we substitute it to get yt, sorry, let me rewrite this. If we want to get yt, if t is approaching infinity, so we get yt is 2/3, because all other terms, which is this term, this term, this term, this term, is exponential function of negative, negative exponential function. So if we replace t with infinity, it will be 1/infinity, right? So 1/infinity is approaching 0, so it is 0. So the term left is 2/3. So we get yt equals to 2/3 for this particular solution of the differential equation that use the Laplace transform. All right. So I have a few other things to finish. So for further readings, you can just have a check in the textbook. For the further reading for different systems, we have mechanical system. So this is the electrical actually, the DC motor system, and then some transfer functions of the circuits that involve the integrating circuit. This is operational amplifier, the motor. This is another mechanical system, rotational, so and so on. And we have the block diagram model. This is actually I'm not going to talk much about this, but you can just have a look at this block diagram model. Is actually we want to use this block diagram model to represent the transfer function so that you can solve for the block diagram of the control system. So we can study about the control system by using the block diagram model. So this block diagram model make it simple if we want to study about the control system. Okay, so I don't have much notes for this particular block diagram model topic, which is 2.6 block diagram model. So basically for this example, block diagram model of a DC motor, you can see it has the input of VF. We apply this input so that we can observe the displacement. So we can observe the theta. So we have the block diagram like this. For the motor, we want to observe the output, which is theta, the displacement. So this is VF, the input, function of S. So if we apply this input, then if we increase this input, for example, for this particular motor, it is turning counterclockwise like that. So if we give this input V, we increase it, it will turn the increase the rotation lah of so theta will be increasing. So the rate of change of theta is omega, right? So all of you know that in mechanics, if we take the derivative of theta, we get omega, which is the angular velocity. All right. So in block diagram model, it's not much, but actually we can consider this. If we have this particular system, I'm going to finish this in few minutes. Let's say we have the transfer function of the block diagram of the control system like this. We have some input and output relationship. So this is summing point. So input is Rs. Transfer function from Rs, we have input of the transfer function of Es and output of the transfer function of the Cs, and it has the feedback block like this, which is this one is Hs, for example. So output from Hs, we have Fs. All right. So this is example of the block diagram for a feedback system. Kenapa feedback system? Kerana ada ni ada feedback. Ada sensor that we use as feedback for the system. So for this particular case, for example, the transfer function for forward path CS, forward path is this path. Transfer function for forward path, which is this part, which is referring to this part. So this one is GS, right? For forward path. How about the transfer function for feedback path? For feedback path, as you can see, the feedback path is HS, right? So HS is Fs divided by Cs. Output Fs divided by Cs of the HS. HS is the transfer function of the feedback path. Okay, and then next transfer function for open loop. So how about transfer function of the open loop? How about transfer function of the open loop? Meaning that we want to combine. We want to combine these two transfer functions so that it becomes open loop. So this example, it is feedback system, which is the closed loop system. So we want to transfer this to open loop system. So what is the transfer function for the open loop system? For that particular case, so it is Fs divided by Es equals to GS, GS, GS and HS. That means we combine GS and HS to become it as an open loop. So transfer function, another one, the last one, for the closed loop, tadi kita ada forward path. Forward path, which is this one. Okay. Forward path, this is this one. Feedback path, which is this one. Open loop, which is this one. Now closed loop. Now closed loop. Okay. So how about closed loop? So it becomes CS over RS goes to GS divided by 1 plus GS HS. So that's it. So we try to simplify this or translate this transfer function block of the closed loop system into another form, which is feed forward path, transfer function for feedback path, okay, transfer function for open loop, transfer function for closed loop, and yes, that is the transfer function for the closed loop. So for further reading, I would like to ask you to follow the notes, make your own notes about this, this DC motor transfer function. How do we get this sort of transfer function? So it is available in the transfer function topic, subtopic. Actually, this is not 2.5, this is 2.6. Okay, so block diagram model also can be considered for the multiple input and multiple output like this. And then we can further, let's say input is I, output is for j's and ith and j's output variable. Ith output variable to the j's input variable transfer let's say if we replace this G11, this matrix with I and J, which is Gij is the transfer function relating to ith output variable to the jth input variable. So it becomes like this. We have Y from Y1, Y2 until Yj. And then this matrix is, okay, matrix G, transfer function matrix, and output, sorry, input R. So we get this form. Actually, in terms of metric, we can just represent it by Y equals to GR. And this is the block diagram of 2 input and 2 output interconnected system. We can also use the block diagram model like this for the interconnected system. Not necessarily we have to follow this system like this. So maybe you will find some more complex system when it comes to modeling the system which is more complex, more consideration of the equation. Okay, so I will finish up to this time for block diagram model. Until I'll see you again. So you can just also consider to study about this combining blocks in cascade, which is this is referring to the block diagram transformation. We can transform the original block diagram to another equivalent block diagram, which I have done before here. Okay, so up to this time, another example, you can just make your own note. You do the self-study. Okay, up to this time, I will finish. Okay, thank you.